Hello everyone, welcome to lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I'm an assistant professor at Concerts University, Islamabad, VA campus. In this lecture, I will talk about the internal architecture of Intel microprocessors, which is also called the programming model of microprocessor. And the discussion will include explanation of flag bits in the flags register of the microprocessor, and the two modes of addressing or modes of segmentation called real and protected modes of the Intel microprocessor. These slides have been edited from these sources given here. A programming model is the internal architecture of a microprocessor, which is actually the structure, an internal structure of the microprocessor, or the number and sizes of the registers in a particular microprocessor. It is important for the programmers, low-level language programmers, to understand the structure or the architecture of the microprocessor. For high-level languages such as Java, C++, it is not that much important to understand the detail of the registers available in that microprocessor. But for low-level languages such as machine language or assembly language, it is important for the programmer to know the uses, names, and sizes of available registers, or in other words, program visible registers. Registers that the programmer can use while designing or developing applications in the assembly language. In the Intel microprocessor, the registers are grouped into three categories. The first category is the general purpose registers, which include these 7 registers: accumulator, base index, count, data, base pointer, destination index, and source index. And these are the names used to reference these registers or part of these registers during assembly language programming. For example, accumulator can be referenced using AL or AX or AH or EX. EAX is the extended version of these registers. The second group is special purpose registers. These 3 registers, stack pointer, instruction pointer, and flags, are the registers that are used for special purpose. General purpose registers are also called multi-purpose registers because they can be used for different purposes. While special purpose registers are for special purpose, they cannot be used for other purposes. We will talk more about these registers and their uses. And the third group is segment registers. There are 6 segment registers. Only 4 segment registers are available in 8086, 8088, and 80286 microprocessor. The 2 registers F and G and the extended part of these registers, which is shaded here, are only available in the 80386 and above microprocessors. This area, which is the 16-bit registers, are available in 8088, 8086, 8088, and 80286 microprocessor, which are 16-bit microprocessor. In modern microprocessors, Pentium, Intel Core microprocessors, and the latest microprocessors are available with 64-bit extended versions as well. The code, these are the segment registers. The first one is code segment register, the second one is data segment register, and this is extra segment register, and this is the stake segment register. There are 4 possible memory segments, and each of the segments is accessed using these registers. For example, the code segment inside the memory is accessed using the code segment register, which provides the 16-bit starting address of the code segment. Similarly, the data segment register stores the starting address of the data segment, and so similarly the starting address for the extra segment is in the extra segment register, and the starting address of the stake segment is stored in the stake segment register. So these are the program visible registers in Intel microprocessor, and these registers are referenced during assembly language programming. To understand the architecture of Intel microprocessor, here is the internal structure of 8086 microprocessor, which is a popular member of the Intel family of microprocessor. It is a 16-bit microprocessor with 16-bit registers and 16-bit data bus, while the address bus is 20-bit. The internal architecture of 8086 microprocessor consists of 2 main units. This unit on the right is called bus interface unit, and the unit on the left side is called execution unit. The bus interface unit is responsible to fetch instructions from the memory and bring them inside the microprocessor for execution. In addition to fetching instructions, bus interface unit is also responsible to read data from the memory and input and output ports. Also, it is responsible to write data to memory locations and to input and output ports. So bus interface unit is responsible to make a connection of the microprocessor with external environment to read data and instructions from the memory and input and output ports. For addressing the segment registers, code segment, data segment, stack segment, and extra segment registers, along with instruction pointer and other registers, are used to generate the address, the 20-bit address, by adding the starting address of the segment and then adding it with the offset address of the segment, and a 20-bit address is calculated. Execution unit is another important unit of the microprocessor. An execution unit is responsible to execute instructions that have been fetched by the bus interface unit. So the bus interface unit fetches instruction, normally 6 byte instruction code that is fetched and stored in the instruction key, and then the instructions are then decoded by the internal control system and generate some control signals, and the instruction is then executed by the execution unit, in particular the arithmetic and logic unit, perform the desired arithmetic or logic operations on the data. Bus interface unit and execution unit can function separately, and they can function independently. For example, while the execution unit is busy in executing an instruction, the bus interface unit at the same time is busy to fetch or load the next instruction to be executed after this instruction which is currently being executed. So This concept is normally called pipelining, and the microprocessor can execute or can process two instructions simultaneously. Apart from other registers, flag register stores the condition of the microprocessor. During the arithmetic and logic operations, certain flags are affected and their values are recorded in the flag register. This is a 16-bit flag register available in 8086 microprocessor. In the later microprocessor, for example in 80286 and above, there is a 32-bit flag register which is called E-flags. In 8086 microprocessor, there is a 16-bit flag register. The first flag on the least significant bit is carry flag. This carry flag is set when there is a carry out of the most significant bit in case of addition or a borrow in case of subtraction. When two values are added, then if there is a carry generated at the most significant bit position, then that is recorded in this carry flag bit. For example, if there is a carry, then the carry flag is 1. If there is no carry, then the carry flag is 0. The same flag is also used during subtraction. When a value is subtracted from the other, if a borrow was needed at the most significant bit position, then that borrow is recorded here. If a borrow was required, then the carry flag is 1. If it was not required, then the carry flag is 0. So carry flag is used for the carry as well as for the borrow. So note that the name is just the carry flag, but it is also responsible to record the borrow during the subtraction. The next flag is the parity flag, which is at position 2. This flag is set to 1 if the lower byte of the result contains even number of ones. If the number of ones are odd, then this flag is set to 0. So during an operation, for example, when two numbers are added, for example, if two 8-bit numbers are added, then the lower byte of the result is considered for the parity flag. If the number of ones in that lower byte of the result are even, then this parity flag bit is set to 1. And if the number of ones are odd, then this flag is set to 0. Parity is normally, there are two types of parity, even parity and odd parity. So the first case is even parity and the second case is for the odd parity. There is a third flag at bit position 4, which is auxiliary carry flag. The auxiliary carry flag is set if there is a carry from the lowest nibble or bit 3 during addition or borrow for the lowest nibble during subtraction. When two values are added, the first nibble, the lowest nibble, which starts from bit 0, 1, 2, and 3. These 4 bits make a nibble. If there was a carry at the bit position 3 for the bit position 4, if a carry was taken from bit position 3 till for the bit position 4, then the auxiliary flag is set. And if there was no carry from the bit position 3 to the upper bit position 4, then it is set to 0. During the subtraction, it is the other way around. If a borrow was taken from bit position 4 for the bit position 3, then it is set to 1, otherwise it is set to 0. In terms of nibble, if a carry was generated at the lowest nibble, the least significant nibble, then the auxiliary carry flag is set. And for the subtraction, if a carry was taken from the next higher nibble for the lowest nibble, then the auxiliary flag is set, and that is actually the borrow during the subtraction. So if we assume that this is the byte, even though this is a flag, but just to consider the bit position 0, 1, 2, 3. So this makes the lowest nibble. So if a carry is generated from this most significant bit of this lowest nibble, a carry is generated at position 3 for position 4, then auxiliary flag is set. Otherwise, it is 0 during addition. In case of subtraction, if a borrow was taken from bit position 4 for bit position 3, then the auxiliary flag is set, which represents a borrow. And if a borrow was not required, then it is 0. Similarly, 0 flag, which is at bit position 6, the 0 flag is set if the result of the computation or comparison performed by an instruction is 0. When two values, for example, are added, and if the sum is all zeros, then the 0 flag is set. And by set, we mean the 0 flag is set to 1. And if the result is not 0, then the 0 flag is 0. In case of comparison, for example, if we compare two values and if the result is all 0, then the 0 flag is set to 1. Otherwise, it is 0. So 0 flag would tell us if the result of the computation or comparison was all 0 or not. There is a sign flag. A sign flag represents if the result of any computation was negative or positive. If the result of computation is negative, then the sign flag is 1. For example, if we subtract a value from the other, for example, we calculate a minus b. If b is greater than a, then the result would be negative with a sign, minus sign, and that is recorded using the sign flag. So the sign flag would be 1. If the result is positive, for example, a is greater than b, then a minus b would give us a result with plus sign. Then the sign flag is 0. So the sign flag would tell us the sign of the result after any computation. There is a trap flag at position 8. This flag, when this flag is set, it enables the debug feature of the microprocessor. This flag is used by the programs to debug code. So trap flag would either enable or disable the debug feature of the microprocessor. So when trap flag is 1, it will enable the debugging facility. If it is 0, it will disable the debugging facility. Similarly, there is an interrupt flag. Interrupt flag causes the 8086 microprocessor to recognize external mask interrupts. If we clear this interrupt flag, it will disable the external interrupts. Interrupt is a useful microprocessor feature when there is a problem in the external devices or internally during the instruction execution, then the microprocessor is informed or interrupted. The interrupt flag can be used to allow interrupts, external interrupts, or to block them. For example, if interrupt flag is enabled, the microprocessor would be able to receive interrupts. If interrupt flag is set to 0, then interrupts are disabled. Similarly, there is a direction flag at position 10. The direction flag is responsible to set auto increment or auto decrement mode of execution. When this flag is set to 0, the auto increment mode is selected. This flag is normally used by the string instruction. For example, when the string data is processed, and if we are interested to process strings starting at the lowest address and then going up, then we would like the addresses to be incremented each time memory is accessed. So this would allow us to process or to access string data starting from the lowest byte, and then we are going up. This is auto incrementing mode, and to achieve this, if we want to process string data starting from lowest address to the highest address, then we have to set the direction flag to 0, and this is auto increment mode. Otherwise, if we are interested to process strings starting from the highest address towards the lowest address, then the mode should be auto decrementing mode. And the auto decrementing mode is set when the direction flag is set to 1. So this flag is extensively used during string instruction when, for example, the data is to be moved from the data segment to the extra segment. Then the destination index and the source index registers are used to provide the offset addresses, and their incrementing or decrementing mode can be set using the direction flag. And finally, we have the overflow flag. Overflow flag is set if an overflow occurs. If the result of sign operation is large enough to accommodate in a destination register, then the overflow flag is set. So, for example, if there is an addition and the addition is 16-bit, while the instruction is trying to store it in an 8-bit register, then this condition is recorded using the overflow flag. So the overflow flag is set to 1 if there is an overflow, when an instruction is trying to store a larger value in a smaller register or smaller variable, then the overflow flag is set, and this would tell us if an overflow has been reached. The flags, the first 6 flags, carry flag, parity flag, auxiliary flag, 0, sign, and the overflow flag are affected during arithmetic and logic instruction execution. Data movement instructions, they do not affect the flags of these registers. In 806 microprocessor, registers are sometimes also categorized into 6 groups. We have general purpose registers. And general purpose register, we have accumulator, base, count, and data. And we have pointer register, where stack pointer and base pointer are the pointer registers. These registers are used to provide offset while creating the physical address. Then we have 2 index registers, source index and destination index registers. There is an instruction pointer register, which is here, which is a 16-bit register, Instruction pointer is a 16-bit register and it provides the offset address of the instruction in the code segment. Then there are segment registers in the 8086, 4 segment registers. These segment registers will provide the starting address of the memory segment. And then there is a flag register, which we just discussed. Flag register would store the program status word or the current state of the microprocessor. This is 16-bit flag register in the 8086 microprocessor. So all of the registers are 16-bit, but some of the 16-bit registers can be accessed as an 8-bit registers as well. For example, the general purpose registers accumulator, base, count, and data are 16-bit registers, but their 8-bit part of the register can also be accessed using these letters. For example, if one is interested to access the low byte of the accumulator, then the name AL is used. If one is interested to access the high byte of that accumulator, then the name AH is used. The same is true for other general purpose registers, base, count, and data. So all of the registers are 16-bit in 8086 microprocessor, but some of the registers can be accessed as an 8-bit, while at the same time their 16-bit part can also be accessed using these names. Even though some of the registers are general purpose registers, but there are some special function of these registers as well. For example, the accumulator, 16-bit accumulator, stores the 16-bit result of arithmetic and logic operations during multiplication, during division. The accumulator is normally used to store the 16-bit result of arithmetic and logic operation. AL, the 8-bit part of the accumulator register, stores the 8-bit result of arithmetic and logic operations. When one is interested to store 16-bit result, then AX is used. If one is interested to use the 8-bit part of the register, then AL can be used. BX, base register, is used to hold the base value in the base addressing mode to access memory data. So the base register is normally used as in addressing, even though it's a general purpose register. The same can be used to store the result of arithmetic and logic operations, but there is a special purpose to provide the addressing or to help in the calculating the memory address. Similarly, CX register can be used in arithmetic and logic calculations, but there is a special purpose of count register, and that is to hold the count value in shift and rotate and loop instructions. For example, if one is to rotate or to loop to a certain label by a particular number of times, then that value is added to the CX register, and each time these instructions are executed, the count register is automatically decremented by 1. Data register, as the name specifies, it holds data for multiplication and division operation. Stack pointer is a special purpose register, and it always is used to provide the offset address of the top stack memory. The starting address of the stack segment is taken from the stack segment register, while the offset address inside that stack segment is provided by the stack pointer register. Base pointer is used to hold the base value in base addressing using stack segment register to access data from stack memory. Sometimes a segment register provides the starting address of that segment, and there is an addressing mode called base addressing mode. So to read to a particular place starting from the offset address, a base address is to be provided, and this base address is normally provided using the base pointer register. The index register, source index, is normally used to provide the offset address of the source operand in the data segment. This is normally used during the string instructions. For example, if string has to be moved from the data segment to extra segment, then the source of the data or the source of string data is the data segment, and the offset address of that um, uh, access is provided by the source index register. And as we already discussed, the starting address of data segment is provided using the data segment register. And finally, there is a destination index register, which provides the offset address inside the destination segment, which is normally the extra segment. This is also used, just like source index, it is normally used during string instructions. For example, move s, which is move string data. There are two modes of memory addressing or memory segmentation in Intel family of microprocessors. The first mode is the real mode of memory addressing. It is used normally in the DOS operating system, disk operating system, and this is the only mode of memory addressing available in 8086 and 8088 microprocessor. And the 80386 and higher microprocessor, they can operate in real mode memory addressing as well as another mode of memory addressing called protected mode of memory addressing. So real mode of memory addressing is only available in is the only available mode in 8086 and 8088 microprocessor. The reason is real mode of memory addressing is the memory addressing mode where only 1 megabyte of memory is used, and in 8086 and 8088 microprocessor, the maximum memory that they can support is 1 megabyte. So there is no other mode, just real mode of memory addressing. In 8086 and 8088 microprocessors, there are 20 bits of address bus, and these 20 bit of address is sufficient to address 1 megabyte of memory. The data bus in 8086 is 16, while the data bus in 8088 microprocessor is 8 bit. There are 16-bit registers in both of these microprocessors. In real mode, the first 1 megabytes of the memory system is called real or conventional or DOS memory. Real mode 20-bit addresses are obtained by combining a segment number, which is the value in either of the segment registers, and an offset address is added with the value in the segment registers. This offset address is normally provided by other registers. For example, in case of code segment register, the offset address is provided by the instruction pointer register. This calculation of the 20-bit address involves or includes the segment register address, which is a 16-bit address, and there is a logically left shift operation by 4-bit position, and that is equal to appending 0 in the hexadecimal or 4 zeros in the binary at the right position. Or in other words, it is also equivalent to multiplying 16 decimal value with the value in the segment register. So there would be a 20, as a result, there would be a 20-bit address, which is the starting address of the segment. Then an effective memory address, which is the exact address of the memory location inside that segment. So the calculation here would give us the starting address of the segment, and then to reach to a specific location inside that segment, the effective memory address is calculated, which is the sum of the 20-bit address calculated here plus the 16-bit offset address in another processor register. For example, if we had to reach to a specific location inside the code segment, then the 16-bit value is taken from the code segment register. That 16-bit value is logically left shifted by 4 positions, so there would be 4 zeros at the right side or least significant position, 4 zeros would be introduced, and this would make a 16-bit address, which is the starting address of the code segment, and then to where from where to fetch the instruction inside that code segment, that address is provided by the instruction pointer. So that value in the instruction pointer is basically the offset address inside the code segment. So that value in the instruction pointer is added with the 20-bit value here, and we will get the effective memory address, which is the sum of the 20-bit segment address plus the 16-bit offset address. And that is the address where the microprocessor has to fetch the instruction from, or to fetch data from the data segment registers or data segment memory segments. For the 8086, segment length is fixed, and that is 2 raised to power 16, which is equal to 64 kilobytes. It is also determined by the size of the offset registers, because the offset value is 16 bits, so the maximum address, the maximum offset address is 2 raised to power 16, which becomes 16 kilobytes. So in real mode memory addressing, the segment size is fixed, and that is 64 kilobyte, and the 4-bit logically left shift would allow us to only define segment at particular addresses. You cannot define segments at arbitrary memory addresses. All the addresses, the 20-bit addresses where the rightmost 4 bits are 0, can be the starting address of the segment. So memory segment cannot be defined at any location. They can be defined at specified locations, and the size of each segment is 64 kilobytes. A protected mode of segmentation. Primarily, what we needed, there are some problems with the real mode of segmentation, and they are that we needed flexible definition of segment starting address. In real mode, the segment can be defined at some set of addresses, but they cannot be defined at each address of the memory. So we need flexible definition of segment starting address. We need flexible definition of segment size. In real mode, the segment can be a fixed size, and that is 64 kilobyte. And finally, we need some protection mechanisms that would prevent programs from corrupting the code and data of each other and of the operating system. So none of these facilities are available in the real mode of memory addressing. Protected mode of segmentation or protected mode of addressing is flexible, and they allow to define memory segment at any location. The segment size is fixed. The segment size is flexible. You can define segments of any size. There can be more segments in addition to the size, flexible segment size, and there are some protection mechanisms or access rights now available with each segment. So some security mechanism is now included to prevent some programs from corrupting the code. So now a program can be allowed or can be stopped or can be forbidden to access certain segments of the memory by setting some access rights or protection mechanism. I will talk about more about these mode of segmentation in coming lectures. If there are any queries or questions while watching this video lecture, please keep a note of all those queries, and you can ask those questions and queries during the online session. Thank you.